Finally, the color of a transition metal complex is also dependent on the ligands involved. So different ligands are going to create crystal fields of different splitting strengths. So we can think of our d orbitals that are splitting into our higher energy orbitals, Eg, and then our lower energy orbitals, 2Tg, of course, being influenced by ligands that are going to control how small or large the energy gap is. And so for our ligands, for example, there's going to be two types that we are going to be focused on. We're going to have strong field ligands and weak field ligands. So strong field ligands are going to lead to a large splitting energy, so a larger crystal field splitting energy, and weak field ligands are going to lead to a smaller crystal field splitting energy. So the question becomes, how do we start to organize ourselves and distinguish all this work? Guess what? Of course, previous chemists have done it for us. Previous chemists have come up with the Spectrochemical Series, which is what you see here, and it will be given to you for exam, so it's not something you have to memorize, but you want to be able to recognize it and, of course, use it in different problems. So using water as our reference, water is going to be seen as a weak field ligand here. And as you can see, all of them here is all going to be considered weak field. And then you're going to have your strong field ligands, which are going to be from our NH3 all the way to our Cn minus. These are going to be all our strong field ligands. So now when you have a specific ligand, whether it's weak or strong, attached to a central metal ion, now you can say, okay, well, how large will this splitting be? We can say, okay, is it going to be large or is it going to be small? So essentially, we use the spectrochemical series for these ligand field strengths here to go ahead and predict the magnitude of our delta amount. And of course, in other courses, you may actually be able to calculate this amount as well. We will not be going into the calculation portion of it. Also, as our crystal field splitting energy increases, higher energy light must be absorbed, okay? So if this entire thing gets larger with our stronger field ligand that we see here, then we must make sure that we are able to absorb the higher energy light. So we're talking about our blues, our indigos, and our violets when we're thinking of Roy G. Biv. And just to be clear, we cannot predict the actual color of a given complex ion, but we can determine whether it will absorb long or short wavelengths, basically, based on if it has an attachment to a strong field ligand or a weak field ligand. And then, of course, we can use that to help figure out the complement colors that it may absorb or transmit. But for reference, when it comes to questions, you kind of want to make sure that you're organizing yourself. So I always say, just to add a little bit of details to all of this, if we run into a situation where, say, the ligands are the same, right? Ligands are the same, so you have to basically find a way to distinguish how these other particular properties can affect this crystal field energy here, right? So we're thinking of oxidation number. If the ligands are the same, they're going to think of oxidation number. And so we know if we have a higher oxidation number, that's also going to equal to a larger crystal field splitting. Also, we can say that if we have a higher period as well. So say we have two metals, they have the same ligands, they even have the same oxidation number. Well, how do we distinguish them? We have to think of the same period that they're in. So say they're in period 4, which has 3d orbitals, versus period 5, which has 4d orbitals. Well, guess what? The 4d orbitals are going to have, down the period, are going to actually have a more positive nucleus, which means they're going to want to attract the ligands more. And when they attract the ligands more, it means more repulsion. So guess what? More repulsion means more splitting, which means a larger crystal field splitting energy. Okay? And there's also several other factors that affect crystal field splitting that we do not go over, like electronegativity, the details of electronegativity from those potential polar bonds, atomic distance, size of ligands, all these little things as well. But for now, let's just focus on what we know and get into some examples to make better connections and start connecting everything as well. Okay? All right, so here are a couple questions. And before we even start, just remember we do have these flashcard moments. That means even in the previous videos, you want to stop yourself in certain areas and make sure you're writing on a flashcard a concept on the front and then something in your own words about that concept on the back to help you actively be a part of the lecture. Okay, so we have these two examples here. The first thing you always want to do is just basically read the actual questions and start to point out any key terms to help us write notes about what we're doing. So I'm just kind of reading this, which of the following complex ions, so I see complex ions, I want to pull that out. Absorbs light, that's something we just learned about. Longest wavelength, that's something we also learned about. Okay, then it says rank, and then it says in terms of splitting energy or crystal field splitting energy, and the energy of visible light absorbed. So again, we're talking about complex ions, absorb light, longest wavelengths. I know I have to relate oxidation number, potentially I have to relate periods of the actual metal ions. I might also have to relate ligand strength. And so I want to bring out my relative field ligand strength that's here. And then I kind of want to just be writing details for myself. So for example, we know we can deal with ligands, and they can be a strong field or weak field. And if they're strong field, they're going to have a larger crystal field splitting. Weak field, they're going to have a decreased crystal field splitting. So what does it actually mean to have a larger crystal field splitting? Larger crystal field splitting means that they're going to have to absorb higher energy. So you can also write absorb. I like to just put everything like higher energy, little acronyms or whatever. And also weak field, they're going to absorb lower energy. Okay? So absorb lower energy or absorb higher energy. Okay, we see that as well. What else can we say about them? If they're absorbing higher energy, that means they're absorbing shorter wavelengths. So high energy, that means we're talking about short wavelength. Low energy, we're talking about long wavelengths. So here, when they're talking about which of the following complex ions, and we know complex ions are going to be a metal ligand that are charged, just to add all those details. Then where they're asking for are going to absorb light of the longest wavelength, they're asking you and telling you that you want to focus on weak field ligands that are going to absorb light that is low in energy with long wavelengths. And so that means I want to focus on weak field ligands. So first, I have to make sure that everything else is consolidated. You have to make sure that we have the same transition metals we're talking about, or at least the same oxidation number. So I'm going through and getting my oxidation numbers for this iron here. So we have iron, Cl is a -1. So we have X -6, which is equal to -3. So we're going to have Fe3 plus here. We also have Fe3 plus here because we also have another -1 charge. We also have Fe3 plus here. We also have Fe3 plus here because the water is neutral. And we also have Fe3 plus here. So they all have the same oxidation number. They're all the same particular element, so they're all in the same period. Now we have to focus on ligands. Now we're focused on weak field ligands, so that means we need to be focused on water and anything over here. If they're strong field, get rid of them. So we can get rid of this one because we do not care about strong field. Now we need to focus on which one is the weakest, because the weakest is going to tell us which one has the longest wavelength. We don't know the exacts, but we can make a prediction of based on our spectrochemical series, right? So we have the weakest being our iodine. So our iodine is going to be letter E, and so that is going to be the weakest, which is going to be the longest wavelength. So that will be the answer for that one. Okay? And that's pretty much what they wanted for that question. Here they want you to rank each of these three complexes in terms of crystal field splitting and the energy of visible light absorbed. So when I think of ranking, I just think of ranking them from the largest crystal field splitting to the smallest. I'm going to say, okay, rank from largest to smallest. Okay. We also got to get the oxidation numbers. We still have Ti here, so we know that we're going to have Ti3 plus here. This is also neutral, so we're going to have Ti3 plus here. This is going to be, this ligand here is charged -1, so it's X -6 is equal to 3 minus. And so we also have Ti3 plus here. So all the oxidation states are the same. Now, if you feel like, wait a minute, you're doing oxidation states too fast, you need to go back and start reviewing those examples more and just practice it more so that you get more comfortable with them. Okay? So our oxidation states are the same. They're all in the same period. Now we have to focus on ligands. We want to rank them from largest to smallest. So as you can see, the strongest is going to be the largest crystal field splitting. You already know that. And so the strongest ligand here is going to be our Cn. The next strongest is going to be our NH3. And then the final one, which is the weakest here, is going to be our H2O. And so that's going to rank them from largest to smallest when it comes to crystal field splitting energy because, of course, the strong field ligands are going to have the largest crystal field splitting energy. And it also is going to rank them as far as the energy of visible light absorbed because the stronger the ligand, then the higher energy wavelength that they have the ability to absorb here. Okay? So of course, to answer this question fully, we would just have to write down all of our complexes in this ring. So this will be Ti, Cn, 6, 3 minus, then it would be Ti, NH3, 6, 3 plus, and then finally it'll be our Ti, H2O, 6, 3 plus. Finally, we can do another one here with the same concept. We want to focus on oxidation numbers. We want to focus on ligands. We want to focus on periods. So let's go ahead and get our oxidation numbers. We have Cr here. So it's going to be Cr 3 plus. We have cobalt here, CO3 plus. We also have Cr3 plus here. And we have Ru3 plus. So the oxidation states for each of them are pretty much the same. Yes, they are different elements. But for this one, because they are all in period 4, then they're all going to pretty much behave the same. Whereas Ru, it is in period 5, so we do have to consolidate that. So for example, our Cr and Cr, they're going to be the same. Our Co, they're all going to be pretty much based on ligands. But our Ru is in period 5, where all of these are in period 4. So that means if we do have to come down to distinguishing, the one in period 5 is going to be the one with the larger crystal field energy. So they said arrange these complexes in order of octahedral splitting energy. They're starting off with the largest here and the smallest. And so we have 4 of them. So let's go ahead and rank these complexes. Again, we got our oxidations. We see they're all very similar. Next, we're going to go off of ligands. So we have strong field ligands and we have weak field ligands. So we have our spectrochemical series here. We have F minus, which we know is going to be weak field. We have weak. We have another weak. We have strong and we have strong. So we have some weaks and some strongs. As we know, because the oxidation states here are the same, then we can just go based off of ligand. These are definitely going to be the weakest or the smallest splitting energy. So we have to distinguish those two. You say, okay, well, if we know that they both have the same oxidation state, well, how do we distinguish them? Whichever one has the weakest ligand. So we're looking at F and we're looking at H2O. So we have F minus and H2O. So that means our Cr, F6, 3 minus is going to be the weakest. After that, the weakest is going to be CO, H2O, 6, 3 plus. Okay? Next, we have these two that both have the Cn minus ligand, which is very, very strong. So the only way to distinguish them is going to be by oxidation state or the period they're in. You see, they both have the same oxidation state, so we have to go off of period. Cr is in period 4, which is a smaller period than period 5. So that means there's going to be more repulsions when you have a larger period, like where you have Ru here. So that means our Ru complex, Ru Cn6, 3 minus, is going to be the strongest complex. And then we're going to have Cr Cn6, 3 minus as our second strongest. So the goal is to basically continue to make all the connections possible between ligand, oxidation state, and of course the period it's in when you're trying to relate it to color, or at least the ability for these ligands to absorb certain colors based on that splitting energy in the d orbitals.